that you want to be careful with. Are we filming? Okay, so we just went over how acids taste sour, which you're not going to taste, turn blue litmus red, and donate a proton. Bases accept a proton, feel slippery, taste bitter, and turn red litmus blue. So, we'll kind of expand on our definition a little bit. As someone also told us, acids are covalent compounds. Lots of our acids are going to behave like ionic compounds. So here, give me a second. Lots of acids behave like ionic compounds, and some truly behave like really covalent things. When you have an acid plus a base, the most common two products you're going to make, does anyone know?
Salt and water.
Salt and water. This is what happens when you have an acid that really behaves like an ionic and a base that really behaves like an ionic. If you have, even though we know they're covalent compounds because they're only made of nonmetals, these guys are going to both behave like ionic things and dissociate into ions when they're dissolved in water. When you have an acid plus a base, and one, or both, but usually one, is truly going to behave like a covalent thing, then you know what you're going to produce? If you don't make a salt plus water, what do you make? Ions. Alright, you're going to make two ions, and they're always going to be two ions that you know. They're not going to be two ions that you make up. They're going to be two real ions, okay, things that you memorize. Something like an OH minus. The only one that you didn't memorize that is a possibility for one of those two ions is H3O plus. The only other polyatomic ion that's positive, a cation, and that is a hydronium ion. Okay? You're not going to, for example, produce an ion that you've never heard of. And there was one practice problem, I think, where if you weren't careful, you might produce something like this. This is not a real ion that you've ever learned about, right? No. So if you take ammonia, which is a base that behaves like a covalent, and it accepts a proton like bases do, then you're going to make the ammonium ion, which is an ion you learned about, memorized, wrote on the chart, have used before. So, if you make two ions, they have to be two real ions, not a fake ion that conveniently gives you a balanced equation without actually balancing the equation. So you can't make it up. You have to, also note that the word salt doesn't mean NaCl, sodium chloride, like table salt. It can mean any ionic compound. There are many, many, many salts in the world, right? You could have potassium chloride, you could have ammonium nitrate, you could have any number of many, many, many kinds of salt. And we'll see lots of them today. Let's see, what else do I need to tell you? So a lot of the time when you are using truly covalent acid or base, some of those examples are things that are amphoteric, which means
they can be both an acid and a base.
Right. So what's an example of something that's amphoteric? Water. So in the presence of a strong acid, and you guys need to memorize that chart of acids and what they're named. So this one, our favorite strong acid, is hydrochloric acid. And in the presence of hydrochloric acid, water is going to behave like a...
The book said we didn't have to memorize that.
You got to know that.
Yeah, they did. Okay.
It would be a shame not to know the names of all those lovely acids. Yeah, please memorize the names of the acids. It'll make your year happier. And I probably use them on the final, and then you won't know what they are. So, we'll use those frequently, and you'll come to know them.
They're relatively easy.
Yeah.
Like from the, like you just kind of
Add an ick.
Yeah, you just kind of like add, I think it's like a hydrogen, since you can just like add a hydrogen or something.
Sometimes you say, but usually you don't say the hydrogen, like if you have this guy, you're just gonna say phosphoric, because that's a phosphate ion, phosphoric acid. Carbonic, that's the only tricky one, the carbonate ion, carbonic acid. And we'll, remind me to talk about polyprotic acid here in a minute too. So we've got water in the presence of a strong acid is going to act as the base. So you've got, well, what do you think you'll make in this case? So remember, if you have a truly covalent acid or base, and in this case you have a covalent base in water, you're going to form two ions.
Well, one of them's going to be the hydronium ion.
Yes. And the other. So if you, this is the acid donating this proton, it forms the hydronium ion. So what's left?
Chloride.
Yeah.
A chlorine. Now what's the chlorine ion's charge?
Negative.
One negative, because it only needs one electron to have a full valence. So, water, because it is amphoteric, it can behave as a base also in the presence, as an acid in the presence of a base. So, let's pick a base. So, for bases, what is something that you'll characteristically see? What kind of ion will you see in the compound name of a base? Hydroxide. So, let's pick, well, sodium hydroxide is kind of the standard base in this world. So if we have sodium hydroxide in water, water can act as an acid in the presence of a base. So what will we form there?
We form ammonium again. I mean, sorry, not ammonium. Hydronium. How do you say it? H3O plus. Right.
Okay, so if water is acting as a base, it's going to donate a proton here. So what will we get? Remember, if water is being an acid, it has to donate a proton, right?
Mm-hmm.
So that one H breaks away, and then what do we get?
The 2H2?
Why am I messed up? I'm not feeling this. I've got a brain
Wait,
clog.
hang on, I can.
Fix my brain clog, somebody quick.
Okay, so you have the H2O, so give the water, give the hydrogen. So then you have the OH, NaOH negative, plus another water, I guess?
You can't do that. Alright, I'm picking a new base in the hopes that I can figure out where my head is and then. Alright, so let's take ammonia. Ammonia is NH3. In the presence of a base, water will be an acid. So water is going to donate one of its protons, right? And you can think of water when it acts like this as an H plus and an OH minus, like it's ionic, even though it's totally not, never ever behaves like an ion.
How do you know when it donates one hydrogen or two hydrogens?
We'll talk about that in a second, but for water, it's always going to split this way into one H and one OH. So when it gives one hydrogen away, what are we going to get here? NH4 plus, the ammonium ion, and then a hydroxide ion. So we have water behaving, in this case, as a base in the presence of a strong acid, in this case, as an acid in the presence of a base. And in both cases, since water is truly a covalent compound, it produces two ions. So Liam's question leads us into, how do you know how many hydrogens it donates? Okay, so water with H2O is not really an acid. It's really, truly all the way covalent. And so it's always going to split into an OH minus and an H plus. But every other acid, like the standard acids that you you. So hydrochloric, hydrobromic, hydrofluoric, any of the strong acids that come from the halogen series, the fluorine, chlorine, bromine, iodine. All of those acids have one hydrogen. Obviously, they're going to donate one. And so when you have one hydrogen to donate in an acid, that acid is called we have one God, so we are what kind of theists? Monotheists.
Oh, polyprotic acid.
Okay, so this is a monoprotic acid because it has one hydrogen. So one hydrogen is going to be monoprotic. Then, let's see, our favorite. The two here. Anyone know the name of this?
That's sulfuric acid.
Sulfuric acid. That's what I decompose that sugar with in the black thing. And only one of these guys I know about. Okay, so when you have an acid with 2 or 3 hydrogens, that gets tricky. Your book doesn't really teach you this. They just have you turn it into this. You just turn this into 2 hydrogens or 3 hydrogen ions. In truth, the first hydrogen comes off readily, the second one not always, the third one really not always. So you end up with a hydrogen phosphate ion. Usually you don't get rid of that third one, but for your purposes, you're just going to pretend that all the hydrogens get donated happily because the math gets to be ugly if you don't, and we're not going to do that to you yet. Not at all this year, in fact. So, when you have more than one hydrogen, those acids are called polyprotic. With polytheists, 2 or more hydrogens. And for sulfuric, it has 2 hydrogens, so it would be
Diprotic. And then another one's triprotic.
And in truth, you don't get complete dissociation of the second or third hydrogen. In practice for us, we're just dissociating them anyway. And that's why I don't use a lot of sulfuric acid in the lab, because I would have to figure out what kind of dissociation to expect so I knew how strong it is. Which leads us down the next road. People say strong acid, weak acid. Okay, so acids whose hydrogens really do dissociate completely are strong acids. The hydrochloric acid is a strong acid. Sulfuric is a strong acid. Its first hydrogen always dissociates, second one usually. So strong acid just has to do with how readily your hydrogen is donated. Okay? It doesn't have to do with concentration. So I could have hydrochloric acid, which is always a strong acid, but I could dilute it with a ton of water, and then it wouldn't be a weak acid because it would still dissociate readily. It would just be a less concentrated acid. So it can be concentrated, it can be dilute, but it's always going to be a strong acid. Vinegar is a weaker acid than hydrochloric acid. It can be concentrated vinegar or less concentrated vinegar, but it's never going to be a strong acid like hydrochloric. Really.
So if a strong acid is diluted, like it won't work as strongly because there's less of it.
Right, there's just less of it.
But it's still a strong acid.
It's still a strong acid in that every molecule of it's going to get rid of its hydrogen and donate it as soon as possible. So, and we'll look at that. We'll dilute some stuff and see what we get there, and see what happens to the pH. You guys don't really. This chapter doesn't cover pH like at all, which is crazy in acid-base chemistry. So pH, I think we do cover it in a little bit, but pH is the scale that we use to tell how basic or how acidic something is. So I'll just give you a quick rundown. Where do we go? Wanda.
14.
It's
Or are
on
you-
14. So 7 is distilled water, perfectly neutral. Anything lower than a 7 is going to be acidic, and anything bigger than a 7 is going to be basic. And the pH scale, just tells us, how, not just how strong the acid is, but also how concentrated, or same for the base. Indicators. So how do we know what the pH of something is?
Do you use an indicator, like, I'm guessing that's red cabbage
Sure is. Sorry, guys.
or fish tank stuff.
Fish tank stuff, so like you dip the little strip in and it tells you the pH of your
It's
water.
like the squirties stuff.
Oh, I never used that. Fish tank stuff. Maybe that's why I don't have fish tank. My 80s clothing is really uncomfortable. I don't like it. I will have more pity on you guys when you dress up from now on. Oh. I think there must be some sort of suspenders that they didn't tell me about from the 80s. Also, these are very uncomfortable. It's weird. Anyhow, so indicators tell us, I would say tell us what the pH is, and since we aren't really talking a whole lot about pH, we can tell if something's an acid or if it's a base. That's gross. It's really strong. I'm sorry if you guys aren't smelling it soon too. So we could test some things and figure out what they are with several different types of indicator. So I've got red cabbage juice here. I have another indicator you'll use next week called phenolphthalein, which I can never remember if it's red in the presence of the acid or the base. I have to try it. And I have some litmus paper, I hope. Okay, so if our definition of acid tells us that it turns blue litmus paper red, and our definition of, oh my gosh, there's something slimy on this. Must be a base. Tells us that a base will turn, I would love to know what it is that's all over me now. I'm afraid to touch the litmus paper now because I might contaminate it all. Let's see. I'm going to lay out a coffee filter to put it on, I think. And then we'll have a look at some things that you probably already know what they are. I'm going to let Maddie get them out so I don't totally contaminate them with whatever slime is on my hands. I'm not hurting yet, so it could just be
All of them?
just maybe 2 strips of each color, please. While I figure out, oh, please God, don't let it do this. It's 15 molar ammonium hydroxide. Not when, I mean, if it was that, surely I would have noticed by now, as my hand would be now really, really soapy. Okay.
Is litmus paper an indicator?
Litmus paper is an indicator. And so we need to really talk about what an indicator is because it's important, especially because there's a test question that's rather confusing, and I really want to make sure we cover it. So we've got some red.
This one touched something.
Well, whatever that thing touched, you can see it turned red, litmus paper blue. So indeed, it is a base. If your hands start to hurt, mine are kind of impervious to everything, so they're not hurting. But if yours hurt, please go wash with water, but probably not soap. All right, so is that red?
That was the blue.
Is that blue? Doesn't look very blue.
That touched something?
No. I have faulty litmus paper, great. Who knows what this stuff is? It's getting bluer.
Did you look behind it?
Yeah, well, I just want to see what I've got. I don't know. Okay, well, we've got what looks like red litmus right there, and I have sodium hydroxide, which we all know is a base. This is a strong base because it's sodium hydroxide, but it's also a very dilute base because it's only 0.1 molar, which we'll talk about here in a minute. So if I drip it onto the red blue-ish colored litmus. Oh, it does turn blue. So we're good. This is red litmus.
This is from the red one.
Well, we could try, this is hydrochloric acid, once again, strong acid but very dilute, 0.1 molar. So if I drip that on the other end, I don't know what will happen. Okay, not a whole lot is happening to this. So litmus paper, not the most awesome indicator, but you can see that the base turned red, litmus paper blue. None of this litmus paper in any way appears to be blue litmus paper to me. It all looks pretty red. So there's got to be a better way, in my opinion. So let's find a way that we can test out not just is it an acid or base, but is it concentrated, strong, weak, of course no trash can, always wonderful. All right, cabbage juice is a great indicator to tell us not just is it an acid or a base, but is it a strong acid or base. Here's what I want you guys to pretend though. Let me erase a little. I want you guys to pretend that you don't know that cabbage juice even is an indicator, okay? So, you have a collection of acids and bases, and you've got this stuff that you're hoping is an indicator. How could you prove to yourself with good certainty that cabbage juice is an indicator?
Pour an acid or a base into it and see if it changes.
Okay, so let's do that. So, put some cabbage juice in here. Now, when you're dealing with acid-base reactions, you don't have to worry too much about measuring exactly how much you're using, because we're just trying to tell is it an acid or a base, not necessarily exactly the right pH. Next week, I'll teach you how to tell exactly how much you're using. All right, so we have pretty similar shade here. This is distilled water, which we know is a completely neutral pH of 7.0. And, yep, my hand's getting slipperier by the minute. So we've got this nice light purple color, very similar. So, Maddie says, well, put an acid in one side and a base in the other side and see what happens. And I'm all for that. That's a great first step. So, if it's an indicator, what would you expect to see?
Change.
Okay, color change.
The acid would turn into more like warmer colors. Or you can send it.
Okay, that's vinegar. So you guys know vinegar is an acid. And what acid is vinegar?
Dilute.
What?
Dilute. Yeah.
Don't know.
Dilute. Yeah.
Well, this vinegar is somewhat diluted. Yes, it's 5%. And it's a somewhat weaker acid than some of the others. But what's the actual name of the acid?
It's really big and long.
What ion is that? So it's acetic acid. It has this hydrogen acetate or acetic acid. And this is ammonia, and ammonia is a base. So if cabbage juice really is an indicator, we would expect a base to do what?
Maybe darker colors.
Or at least something different than the acid. And thank you for getting the paper towels, Micah, because spill one. Okay, so is this enough to tell me, yes, cabbage juice is an indicator?
Yes.
No. And here's where we get the test question wrong. So this is why we're doing it this way instead of just demonstrating happy little acids and bases. And probably the most missed test question of the year, even when I tell everybody this. But you guys always do a great job, so I know we will do. So what if it had just been a fluke, a weird chemical reaction, just a happy accident that it reacts that way? How do I make sure
You do it multiple times.
with...
Different acids and bases.
Okay, so if I pick another acid and another base and I get the same results or similar results, then I can start to have some confidence that this is really an indicator. So if I find another acid to go on the pinker side and another base to go on the greener side, then perhaps we're looking at a don't want that one. So I have this dropper bottle of hydrochloric acid. So I'm going to put some of this in here. Oh look, hydrochloric acid did the same thing as vinegar. And we've got pink. Now note that I put much less hydrochloric acid than vinegar, and I have a slightly darker pink. So that might tell us something. And in fact, maybe I'll stick a little more in there just so we can see what happens to a stronger acid. Okay. So hydrochloric acid is our strong acid, vinegar. Maybe I'll leave this one just so we can see what neutral looks like. Ammonia turned it green. So what if we try a couple more bases, see if we find the same results. And I diluted a little bit with distilled water also, just so we can actually see the color change. It's not such a dark purple that it kind of conceals everything. Let's see. Also have to figure out how to lie out, because I didn't think I have a spoon, do I? Okay, so lye, green, really fast, really green, actually hot too if you want to feel. When you dissolve a strong acid or a strong base, it gets hot. Remember, is dissolving a chemical reaction or a physical change? Is dissolving a chemical reaction? Dissolving is a physical change, so why do I have a heat change? That's usually something that you see with a chemical change.
What does the molecule say?
So there is some heat of solution or heat of dissolving here, and even though it's a physical change, strong acids being diluted with water, strong bases being dissolved or diluted are going to show a heat change, which I think we actually know that's an acid-base reaction we do calorimetry with again later. Now this one will be a little bit wonky because mocha magnesia is kind of a white chalky stuff instead of a nice clear liquid like the other acids and bases I chose. But, okay, so another lab technique. Should I just stick my dropper in there and get some? I did do that with the lye, but really what you need to do is to pour out in a tiny container or something a little drop of your sample.
But you don't want to pour out lye anywhere.
I'm not planning to. So sticking that in there, yeah, I really didn't want to pour out the lye. Sticking the dropper bottle into your stock bottle is called contaminating the stock. You never want to stick